Okay, so there is your homework, and part of the packet of notes that goes with this video is 2 more pages of worksheet 1, and I call them the chapter 33 pages, even though they're still part of the big packet worksheet 1, but they relate to the topics in chapter 33 in your book. Only do these few problems. The rest I will assign after the next video. Only do that problem from what is listed. You can do everything that's listed in chapter 28.4 because today's video only gets through some of the chapter 33 stuff. So these are the 2 pages that I'm referring to there. Also, part of the packet for this video is the answer key for gender politics. So make sure you check your answers, understand all 3 ways for checking for independence. If you have any questions on that, of course, come to my WebEx office hours. The other thing, actually the thing that we're going to start with in about 1 minute, is this page. It's a word problem about the Zika virus. So if you'll pause the video and just take like a minute to read through that, then we're going to talk about it together. All right, so remember last video, we had data tables, and that's why the gender politics, we had a data table, we answered probability questions, then we checked for independence. This video, the other part of chapter 28.4, is the backwards order. They're going to give us probabilities, and we have to actually construct the data table, and that's what we're going to do for Zika. Quite a few more really good problems in chapter 28.4. I know there's a problem about supporting vouchers for schools. I think there's another one about a drug test. It's really important. Maybe I should have put a star here. It's really important you do those problems because I did not include any of those problems in worksheet 1. So that's the only place that you're going to get practice on those. All right, but let's do this Zika one. You know, I usually sometimes prefer to start with the drug test because I think we're a little more familiar with drug testing. So let me just ramble about that for a minute. You know, any type of test, whether it's a drug test or a test to see if you have Zika or a pregnancy test, right? There's 2 ways that it's done correctly. A drug test. If you do drugs, well, the test should come back positive. If you don't do drugs, the test should come back negative, right? But then there's always 2 mistakes. If I do drugs and the test comes back negative, that's actually called a false negative, right? I'm probably going to be happy that I didn't get caught, but my employer is not going to be happy. Then, of course, there is the if I don't do drugs and my drug test comes back positive, that's a false positive. That's a lot of problems. I might get fired and I don't know why, that type of thing. So any type of test always has an accuracy rate. Like, you know, if there's a drug test that's 95% accurate, we all, and also many doctors, make the wrong assumption that, oh, yeah, 95% of the time, it's going to do everything correctly. Or if I test positive on a drug test, most people are thinking, yeah, there's probably a 95% chance that she does drugs then. That's not exactly what any of this means. So Let's do the Zika one. 98% accurate. So that you're very careful to give you the definition of what that means. If someone has the Zika, the test will be positive 98% of the time. Given they have the Zika, the test will be positive 98% of the time. That is actually a conditional probability. Given you have Zika, what's the probability your test will be positive? 98%. And if someone does not have Zika, well, hopefully they get a negative test, right? 98% of the time. So we understand that. It's the other direction that gets confusing. What if I have a positive test? So this is more intro. You don't have to write what I'm about to write over here. What if I get a positive test? What is the probability I have Zika? That is not that. Those are two completely different probabilities. So, and this is like a picture. You go to the hospital, you have a positive test. What are you naturally going to think in your head? Oh my God, I have Zika, right? That's what all of us are going to think. Or turn it into a drug test. If someone hears that you had a positive drug test, you better believe that everybody's going to assume you do drugs. Because they're thinking that this is 98%. Well, we're actually going to figure out what that is in a minute, but we need to set up our table first. Now, of course, these tables right now are based on some initial assumptions. Let me first do that again. I just needed more room, sorry. Okay, that's what I had written earlier. I just wrote it smaller. Okay, the CDC recently reported that 0.5% of the population actually has Zika. Please turn 0.5% into the correct decimal, 0.005 or 0.5%, whichever form we're going to need. Okay, see, this is even prompting you on the imagine. Imagine you've taken the test and he tells you you're positive. How concerned should you be? Meaning, what are you going to think? Oh my gosh, I absolutely have it? Well, we'll see. All of these contingency tables, you really need to start with some initial population. This one says to use 10,000. Now, you might think, well, that's pretty random. Aren't things going to change if it were 100,000 or a million? They're actually not, because this is all proportional. The only reason most of the time we use 10,000 is just so we don't have ugly decimals. And if you're not convinced of that, once we do this problem, redo the problem with 1 million in the population, and you will see you end up with the exact same percentages. Now let me recreate my table so it looks like what's on your handout. Has Zika, no Zika. Okay, we're starting again, just had to pick some number. It's all proportions, so it doesn't matter. 10,000. Okay, what do we know? Well, we know 0.5% has Zika. That's this number right here, right? You got to figure out what 0.5% of 10,000 is. That's where that decimal is going to come in very handy. 10,000 times 0.005. You should get 50 here. Make sure you understand that before we keep going. Well, okay, then in 10,000, 50 would have Zika. So then how many don't have Zika? Well, 10,000 minus 50. Okay, so I did some multiplication to get that number, but this number I just subtracted, right? Because those two numbers have to equal that one. All right, now what? Let's work with this guy up here. Given you have Zika, 98% of those with Zika will test positive. 50 times 0.98. Let me say that one more time. Given you have Zika, those 50 people have Zika, right? Those 50 people have Zika. Given you have Zika, 98% should test positive. So 98% of 50 is 49. Well, 49 plus 1 gives me 50, so then I can just do my subtraction to get the 1. All right. This guy, no Zika. The 9,950 people do not have Zika. 98% of them should test negative. So 9950 times 0.98, 9751, and then subtract it from 9950 to get the 199 here. Now let's add across, finish up our numbers, and we're also going to check to make sure we did everything okay. 9752 plus 248 does equal 10,000. It just kind of helps, save some silly mistakes. All right. There are 2 questions on this piece of paper. I want to do the second question first because that's the most important. You're sitting at the doctor's office and the doctor comes back and says, your test came back positive. You and your family are going to automatically assume, oh my God, I have Zika. Is that really what's happening? Given you got a positive test, what is the probability that you have Zika? Given you got a positive test, 248 people got a positive test. Remember, that's the given part that goes into the denominator. So I'm having tunnel vision for this first row now. How many of those have Zika? 49. What is 49 divided by 248? 19.76%. I really want to make sure you understand this because this is so real life. Again, drug test, pregnancy test, tests for different diseases and viruses. This is real life. Now, again, there were initial assumptions, right? The initial assumption of how many people in the population had it and how accurate the test is. Obviously, you need to know those 2 pieces of information. But look at this. When you hear that a test is 98% accurate, when you get a positive test, actually there was less than 20% chance that you actually had Zika. That's crazy to think about. Crazy. The drug test one you're going to do for homework doesn't turn out that bad because more people do drugs. So, this initial assumption of how prevalent it is in the population, of course, is important. So this is pretty rare, unlike people who do drugs. But under these initial assumptions, that's a pretty crazy number to think about. So that's your second one. The first one was, what's the probability given you have Zika? So here's your answer for the first one. So the answer for the first question is 0.98, 19 or 98%, whatever. That's your answer to the second one. We had already kind of done the first one. I had already done that. I didn't even realize it. All right, so that's pretty cool, especially when you do the drug problem, because I think those numbers are, I think it assumes 4 or 6% of the population does drugs. All right, Zika's done. Oh, before we go into starting the new topic, chapter 33, I just wanted to do an extra word problem just to kind of help you out. So once I write it up, if you want to pause the video and take 5 minutes to do it and then come back. I don't even have the answers. I'm going to have to do it with you. We're just going to call this extra. Just sort of a check-in of how you're doing with those word problems on worksheet 1, like number 1 through 13, I think. So let's just say 40% of JNU students have a meal plan. I'm going to ask the next 20 students. So here are some questions we want to ask. Maybe we'll do 2 parts at a time. So pause the video, go do these 2, and then come back. Okay, so more than 19 have. Well, you got to think about what numbers are more than 19. Oh, it's just 20. See, it's not a lot of things. It's just the all case. 20 have. You could put 20 little checks in a row. I'm too lazy to count. Pretend there's 20 there, right? Having a meal plan is 40%. Have is 0.4, not have is 0.6, right? So this is just 0.4 to the 20th. This is fairly easy. There is no reason, no, I need to re-clarify that word. You absolutely are not doing a 1 minus. Also, this gives you another chance to make sure you understand what your calculator's giving you. I do not accept scientific notation. That's the full answer my calculator's giving me. It depends on your calculator. No matter, you have to make sure you understand that this is approximately 0. I've left these 2 up at the same time for a reason. Let's do this one. At least 1 has. Well, you got to think of what at least 1 means. It means 1 or 2 or 3 or 4 or 5. Oh my God, all the way up to 20. I'm overwhelmed. Whenever I start to get overwhelmed, I'm like, I better make a chart. This problem was about having. So that's why I put have as the title. All you have to do is show the first 2 and the last 2. Remember, this column is representing the probabilities, even though I don't know what they are. This problem wants you to calculate and add up all of those numbers. Well, there's no way. That's impossible. I haven't taught you how to do that. So this jumps out at you as, yes, this is a 1 minus. 1 minus what I don't want. 1 minus what did I not circle. 1 minus 0 have. Oh, there's my sigh again, right? We can't do the 0 case. Every time the 0 case comes up, we have to come up with the synonym. 0 have is all don't have. Like 0 girls is all boys. 0 remember is all forget. 0 pass is all fail. 0 have is all don't have. Oh, I can do that. Don't have, don't have, don't have, don't have, don't have 20 times, right? What is don't have worth? 0.6 to the 20th. If I put that all into my calculator at once, depends on your calculator. You don't need all of these decimal places. I'm just trying to show you, I think it goes out even further. The bottom line is this is approximately 1 or 100%. The reason why I put these up, again, some students decide in their head, oh, if I see the word more than or greater than, I know it's a 1 minus. No, you don't. Look, this had the word at least, and this had the word more than. This one did not need a 1 minus. This one did. So until you start actually thinking about the problem, translating it, asking yourself, what does that mean? What does that mean? Oh God, it means a whole bunch of stuff. That's the way you're going to decide if you need a 1 minus. Again, if you had right on this problem, hadn't really, maybe you didn't know if you needed the chart or not. So let's just pretend you had made the chart because you didn't know. More than 19 is just 20. You would have only circled one thing. When you circle one thing, that's not a 1 minus. That's just do it. Okay, let's add a C and D to this. Same problem. So part C is probability only John, Sue, and Mary have a plan. Part D is only Chris, Martin, and Chloe have a plan. So you got to make sure you understand what I'm not asking you. I did not ask you what's the probability 3 people have a plan. I haven't taught you how to do that. I teach you how to do that in the next video. I actually named the people. Imagine there's 20 people in front of you right now, and you happen to know all 20 of their names. You're going to know exactly which 3 people I am talking about. John has a plan, and Sue has a plan, and Mary has a plan. Well, there's 17 other people in the room. So you know that those 17 people, I'm just too lazy to name them, right? Those 17 people do not have a plan. So it's going to be very helpful if you start to understand. We're going to put that in the calculator. 3 people have the plan. 17 people do not have the plan. Remember how we can look at the exponents to make sure we took care of all 20 people? Let me figure out what that is. Okay, so this one is going to be approximately 0. I just want to make sure you understand. It's e to the negative 5. I only require 4 decimal places, so this is approximately 0. But again, in a testing situation, you don't get to just tell me 0. This part is really the part that tells me you did it properly, because you can get the answer of 0 having done it completely the wrong way. So I really need to see that part, right? Well, look what I did here. All I did was 3 different people. It's the same thing. Any 3 people I name, it's going to be the same answer. Okay, so now we're going to kind of completely switch gears and start talking about counting principles. Like, have you ever wondered how many different license plates there are at DMV? Or how many different phone numbers? Or, gosh, I was texting one of you guys a few weeks ago. I'm almost positive you told me you lived in Northern Virginia, and I had never heard of the area code before, meaning it was not around when I was growing up. I think Virginia Beach is trying to get maybe a new area code because they're starting to run out of phone numbers. So have you ever thought about, oh, how many phone numbers can you have? Or passwords. You know, we have to change ours so many times for JMU, and then there's special characters, and there's all this stuff just trying to keep the hackers away from trying to guess our passwords. All right, so we're getting into chapter 33. Stuff we do today is the easier stuff. Next video is the harder stuff. So we're going to start with, like, we're in elementary school right now. And because sometimes all of us adults, you and me, will overthink the elementary school problems. So, here's the deal. You have 3 pants, 2 skirts. We're not being gender specific. Think about, hey, isn't it Scottish people or something that wear, men that wear skirts, called kilts? 3 pants, 2 skirts, 2 shirts. How many outfits can you make? Let me say, we've done this with kindergarten and first graders. We actually quickly drew up little pictures of pants and skirts and shirts, and we had the kids color multiple copies of them, right? Like 2 different colors on the skirts, 3 different colors on the pants. We had them work in groups, and we put them in where they're these big tables, and we actually had them construct the different outfits so they could visually see them. And that way they would know that they hadn't repeated it. So you can easily do this with die cuts. We're not going to do that. So there are some assumptions here. You're only putting on 1 bottom. There used to be a fashion where the girls at JMU would put a skirt over top of the pants. We're not doing that. This is just classic. You're going to look normal. You're going to have 1 top on and 1 bottom. Pause the video right now. see if you can figure out how many different outfits, because I wanted to show that there's at least 2 ways to get organized here. Either way is perfectly fine, but just so you'll know which way maybe you were drawn to. So pause the video, maybe some type of quick little tree diagram or whatever type of picture you would like to make to figure out how many outfits. Okay, so some students do it like this. They think of the bottoms. They've got pant 1, pant 2, pant 3, skirt 1, skirt 2, and then they have the 2 shirts coming off of each, right? So you can easily see that you have 10 outfits. That's the right answer. Other students will split it up. They're probably kind of viewing it maybe a little more gender specific or something. I don't know. They'll do the pant 1, pant 2, and pant 3, and they'll have shirt 1 and shirt 2 coming off of each one. I'm just trying to give you a skeleton right now, right? So they see there's 6 on that, but then they'll do the skirt 1, skirt 2, each of the shirts coming off of that. They'll see they have 4 more, which equals a total of 10. So those are probably, I mean, you could start it with the shirts also, right? But those are 2 of the most common tree diagrams I see when I walk around the 207 classroom. So there are 10. Basically, again, tree diagrams and doing these activities with the younger kids is getting them to understand when we work them up to a formula. Listen, you got 5 bottoms and 2 shirts. You can just do 5 times 2, which is 10. And this is actually a particular rule. So that's what I'm going to put up in a couple minutes, but we're going to do a few more real problems first. Through the years, I've seen so many commercials for restaurants. I think it was Ruby Tuesday or Applebee's. I always get those two confused. I think it was Ruby Tuesday that one time in May they advertised, we have a special summer menu. Come in every day during the summer and you'll be able to eat a different meal. And they were defining summer as Memorial Day through Labor Day. It was something like there were 90 different meals. So I went on the website to actually see how they were going to provide me 90 different meals. And you start to realize it's a little bit, I can't say false advertising, it's misleading. I've seen the same thing with Olive Garden. Cracker Barrel does not advertise it, but they actually could. So if you're doing this with your kids, go collect some of the commercials or even some of the menus at the restaurants, because all the restaurants seem to have some part of their menu that's like, pick an entree, pick a side, pick a dessert, where you kind of create your own combo type thing, and then have the kids figure out how many different meals you could make. So let's do Olive Garden first. This, I'm almost positive I wrote down the correct numbers off of an advertisement a couple years ago. They were advertising that there were 50 combos that you could make in this special section of their menu. I mean, they have a much bigger menu, but this was like all for like $9.99 or something. So when I went on their website to see, okay, for the $9.99, what do I get to get, right? I got to pick from the 4 soups or 1 salad. I had to pick one from there. That was kind of put in a pile together. That was like, I guess you'd call your appetizer or something. And then there were 10 entrees, and you got to pick one of those. So 4 plus 1, yeah, 5 times 10. Okay, that's where they got their 50 from. They're not lying to you. But here's my position or my opinion, and again, a little more fun when we're in the classroom so you can give me your opinion. For me, I'm not sure that I'm going to feel like I had 50 different meals. Most of us, it's the entree that kind of is the main thing, right? So we feel like we're eating something different. I'm not really sure just having a different soup beforehand if it's going to make me feel like I really had a completely different experience. I would say for myself personally, that's about 10 choices, not 50. But that's how they were able to create this so they could advertise on TV 50 different combos. That's almost 2 months worth of going in there every day to get something different to eat. But it's really only 10 entrees. All right, now again, I have never heard Cracker Barrel advertise this, but I do know on their menu they do have a create your own plate or something, grandma's plate, I can't remember. I did not feel like pulling up their menu, so just go with me here. Let's say there are 4 entrees, 6 sides, and 4 desserts. And you get to pick one of each. Let's pretend this is lunch. We're not going to overeat at lunch. How many different combos could they advertise? Well, 4 times 6 times 4, which is 96 different lunches I could have. You better believe Cracker Barrel could advertise that, and it would not be a lie. But look, do I really care whether I got green beans or corn or okra, right? Do I really care whether I got a chocolate chip cookie, scoop of ice cream, or a brownie or whatever? Most of us really view our meal as the entree. So somehow 4 entrees suddenly morphed into 96 different meals. This is how they can advertise. All right. This idea of multiplication has a name. It's called the fundamental counting principle. I think it's on page 811 in your book. I'm going to word it the way your book words it because I want to pick on it a little bit. Basically, it's the multiplication rule. You just multiply them, right? If activity 1 can be done in M ways, and activity 2 can be done in N ways, then activity 1, activity 2 is M times N. First of all, I hate when books use M's and N's because I can't pronounce them very well. Secondly, I'm going to be honest, the very first time I read this in your book, I thought they meant the subtraction sign. I thought they had made an editing error. It really freaked me out. They're using that as the dash to do activity 1 dash activity 2. So I just want to make sure that nobody gets confused on that to think that you're actually like subtracting something. That's just a dash sign. So, all right. Dominoes. Let's talk about Dominoes. I'm going to keep this short because I could probably spend 45 minutes talking about Dominoes. I also Googled and researched Dominoes way more than you can ever imagine. And you would be surprised, there are crazier people than me. There are massive discussions about how many different pizzas from Domino's because a couple years ago, Domino's had a commercial. I don't remember now. It was something like 1 million pizzas or something. And everybody was wondering, well, what initial assumptions is Domino's making? Nobody ever really exactly figured it out, so there's, these are the math nerds, right? So many people writing pages and pages of, well, if they're using this, this, and this is how many pizzas you can make, or if these are the initial assumptions. We're going to do a much more simplified version of Domino's. So we're going to call this the simplified version, meaning this is not real life. I did take a look at their online ordering one time just to try to get some idea. They have a lot of different crusts. I also thought it was interesting when I looked at the sauces, you actually don't have to put sauce on your pizza. There was a no sauce choice. Then there are different amounts of cheese. We're just going to kind of go with regular and extra. And let's just say there's 10 toppings. I'm pretty sure there's a lot more than that, but let's just say there's 10, okay? Now, you can order any pizza you want with any amount of toppings. Now, we're not even getting into the idea that you can split your pizza, half one thing, half another. Again, we're keeping this simple. But everyone tried to figure out from Domino's, we do not think they limit you on how many toppings you can put on your pizza. Of course, they're going to charge you extra. I mean, if you put all 10 toppings on your pizza, that is not going to be a cheap pizza. But with any amount of toppings, see, the beginning part's easy. Crust. There's 5 different crusts. 5 sauces or no sauce. That's really 6 different choices, right? Then the 2 amounts of cheese. But now here's where it gets kind of funny. What I'm about to do, you probably would have never have thought to do on your own. And guess what? Neither did I. I actually read this trick in your book. I'm like, oh my God, that is so cool. So, sometimes the things I'm giving you is, again, I'm sort of, the tricks in your bag. It's experience. I'll never forget it now. Once I, read the trick, I'm like, oh my God, that is so cool. What am I talking about? See, it's a really complicated problem if you think about it like this. Well, I'm going to have to figure out how many ways to make a pizza with just one topping. Then I'm going to have to go figure out all the different grabbing 2 toppings. Then I'm going to have to figure out how many, different ways to put 3 toppings, all the way up to 10. You'll be here all day if you're going to do it that way. So here is a pretty cool trick. Imagine all 10 toppings, like pretend you're at a buffet or something, right? And you're walking down, picking out your food. 2, 4, 6, 8, 10. So let's say you've got your pizza and you're standing here in front of all 10 toppings. They're in front of you. You're about to build your own pizza. Let's say, this is like pepperoni, mushrooms, onions, green pepper, olives, whatever, right? When you get to each topping, you can kind of ask yourself, do I want this or not? There's really 2 choices. You're either going to put the pepperonis on your pizza or not, kind of like with the sauces. So there is 2 choices for each, because on each one you're going to decide, do you want it or not? So what do we have now? 5 times 6 times 2 times 2 to the 10th power. I thought that was a pretty cool trick when you just have to think about it, do I want it or not? Just on this simplified version, you have 61,440 pizzas. I'm not convinced they're all going to taste good, right? And this was a much simplified version. All right, let's do 2 more problems. This was probably one of the trickier ones, but it's a pretty cool trick in there, right? Let's go back to outfits. It's not hard, but we have 6 pants, 10 shirts. Now we have 2 belts and 4 ties. I stole this from some book, but they made a point to say that the belts and the ties are optional. We're assuming pants and shirts are not optional. We need you to be covered to walk out into public, right? So 6 times 10 is the easy part. Now, let's say the belts. I have the brown belt, I have the black belt, or I have no belt. Or if you want to think about it, call it the invisible belt, right? So for belts, there's really 3 options. The 2 belts, and then no belt is an option. It means your pants are going to fall down, right? Okay, 4 ties. Tie 1, tie 2, tie 3, tie 4, or no tie. So that optional, or if you want to call it the invisible tie, is an option. So instead of using the 2 and the 4, we're going to use the 3 and the 5. This suddenly gives you 900 outfits. Now, depending on if you're a person who's into clothing or not, 10 shirts, I'm not really sure that I'm going to think about that I have 900 different outfits. This is a fun little thing. You could have your students go home and count up how many shirts they have in their closet and how many bottoms, and have them calculate how many different outfits, and to show them they don't need to buy new clothes. Although, of course, there's the argument of a lot of that stuff wouldn't match. It doesn't go together. I don't like half the clothing, whatever. But, outfits and clothing with kids, it can really get them involved in the discussion, particularly if you have them, go gather some data from home. All right, let's do license plates. Now, the fun part about this, so, I have 4 daughters. I'm telling you, none of them really liked math as much as I tried to get them into mathematics and, real life stuff. So I don't have a bunch of math geeks at home. But when they were young, I was always beyond thrilled, as you will be with your own students in the classroom, when something organically comes up. So this is about license plates. Many years ago, we were sitting in the car at a red light, and one of my daughters was pretty young. She was staring at the car in front of us, and she just kind of happened to say, she was asking me, she's like, well, can 2 cars have the same numbers, the same license plate? I said, no. I said, now, we're in Virginia. I said, someone in North Carolina might have the same letters and numbers as someone in Virginia, but a Virginia license plate is different than a North Carolina one. So I proceeded to probably tell her more than she ever wanted to know. But she then said something like, oh, wow, there must be a lot of license plates out there. And I said, well, let me calculate that for you. We're also going to bring in some history here. So somewhere in the last 20 years, things have changed. I don't know the exact date, and I am talking about Virginia now. We're talking about standard issue license plates, not specialty ones, not design your own, nothing like that. So I'm just going to call this the 1970s versus now, okay? When I was growing up, it was 3 letters dash 3 digits, 3 numbers, right? Now, if you could just go look at a basic Virginia license plate, it's 3 letters dash 4 numbers. All right, and I don't know if there's any restrictions, if I know you can't spell bad words, but I didn't feel like looking all that up. Let's go with how many. So there are 26 letters in the alphabet, so you can put your 3 dashes, 26 times 26 times 26, and then there are 10 digits, 0 through 9, times 10 cubed. That should give you 17,576,000. Currently, there are approximately 8 million people in Virginia. Given that I'm sure all those license plates aren't valid and you have work vehicles and all that, I think at some point they realized we need a lot more license plates. So that's when that extra digit came into play, right? 10 to the 4th. Not a hard problem. The numbers just fascinate me. It's 175 million. Well, of course it is, right? Because 17 million times 10 is 175 million. Something like this, you can bring in so many other curricular activities. The idea of estimating people in Rockingham County, people in the state of Virginia, people in the United States, people in China, people on planet Earth. I'm telling you, adults cannot even give a reasonable estimate of those numbers. I've had students do projects where they ask other JMU students. We've had students think there's only 10,000 people in Rockingham County. We've had students think that there are 1 million people in Rockingham County. Both of those are a bit off from reality. I'll put it that way. But I love this. Big numbers. We have a very hard time wrapping our minds around them, right? Just putting 1 extra dash on the license plate, having 4 numbers instead of 3, we go from 17 million to 175 million. That fascinates me. Pretty sure we're not going to run out of license plates under this model, right? I understand math, and I understand that, yes, 17 million times 10 is 170 million, whatever. It still fascinates me when I think about just one extra spot gave that many more, that power of 10. See, when you go from 10 to 100, that's not very interesting. 100 to 1,000, still not very interesting to me. When you go from 17 million to 170 million, that fascinates me. So just giving students number sense, I think, is so important. And you can also then research populations, population growth, all of that type stuff. So, all right, that is it for this video. Next time, we're going to get into harder counting techniques called permutations and combinations. So if you have not read chapter 33.2, please do so, because that stuff is definitely trickier than what I've done today on this video. All right, see you soon.